Hi viewers, today we are going to see smart polymeric materials in that special type PVDF. Okay, I am Dr. Asrika, Associate Professor, RMK Engineering College, Chennai. Let us get into the topic. PVDF, okay, polyvinylidene fluoride. This act as a piezoelectric material, best piezoelectric material, widely utilized in all applications. How it is synthesized? First, we'll see the synthesis of this PVDF. PVDF is produced by free radical polymerization of monomer vinylidene difluoride. Okay, this process occurs in presence of temperature 10 to 150 degrees Celsius and subjected to a pressure of 10 to 300 atm. So we get polyvinylidene fluoride. You can see the equation here. Uh, Material is processed and fabricated into parts by lot of different methods of casting. One is melt casting, solution casting, spin casting, and film casting. Any of the method can be used to form the material, polymeric material. In this PVDF, we have found that there are different forms of PVDF, right? So here we have alpha phase, beta phase, gamma phase, even people say we have delta phase and epsilon phase. 5 different phases are found in that. These three are the most prominent. Okay, so what is the structure of this phase? See, any smart material, the basic structure decides its property, right? So alpha phase and gamma phase do not show any much piezoelectricity, but the beta phase of the PVDF shows a piezoelectric property. You can see in the figure, right? So what is alpha phase? How it is structured, right? The blue one is fluoride and red one is hydrogen. So this fluorine and hydrogen are responsible for this piezoelectricity. The presence of fluorine and hydrogen atom are responsive for the piezoelectric properties. See how it is arranged in beta phase. All red are one side and all blues are on another side. All hydrogens are one side, all fluorines are on another side. See here, I have represented even in the form of your chemical form where we can see all hydrogen, so gives you positive charge, all fluorine, it gives you negative charge. If you remember in my previous lecture, I showed you piezoelectric property. They exhibit on the surface positive signs and negative signs, right? So positive sign here in PVDF is because of hydrogen and negative sign is due to fluorine. Okay, in gamma phase, you can see the structure, how it is structured. So in this case of structures, they get cancelled out. Blue and red get cancelled out, this plus and minus, and they behave neutrally. But in beta phase, they show this piezoelectricity. See, we have another structure here to for better understanding before applying a pressure, how this positive negative signs are aligned. Okay, when you apply a pressure, so they are mostly aligned, and at the surfaces, you can see one side you have full negative charges, on the other side we have full positive charges. So this develops the piezoelectric property, or we can develop a potential on applying a mechanical stimuli. Piezoelectricity of PVDF. As we saw the figure in last slide, that beta phase is responsible for the piezoelectricity. What happens here? The positive and negative charge as a material, it is balanced and it gets cancelled and net charge is nullified. Okay, but when a pressure or mechanical force is applied, this balance gets disturbed. Okay, and there appears a net charge on both the sides of the crystal generating a voltage. Okay, in the side figure, you can see that, I'll take the pointer. You can see that we have stretching the force, we have tensile force, and this is compression force. When we apply this force onto this, we can see there is a generation of potential on the sides of the surface of the material. One side we have positive, another side we have negative. So there is a potential generation or voltage drop. Okay. So this side also, when the phenomena is opposed, see, one is tensile force, another one is compression force. When the phenomena is reversed, you can see the polarity changes. This side we have minus, the other side we have plus. And the phenomena is same. Whether you compress or you stretch, the property is observed. Piezoelectricity property is observed. In the second diagram, first one is vertical force application, second one is horizontal force application. Again, it is a stretching or it can be a bending. And okay, so in this case also, the opposite force, the polarity changes. Okay, because the phenomena is reversed, right? So polarity changes. Then piezoelectricity depends on the electroactive phase and crystalline phase of PVDF. Okay, this it depends on that phase. And how this piezoelectricity is induced in PVDF, this is heated to a temperature of plus 175 degrees Celsius, and the polymer is stretched to a high electric field to generate piezoelectric property. Okay, PVDF generates an electric charge in response to temperature variations. Okay. Then properties. It has excellent abrasion resistance. It is piezoelectric, pyroelectric, and good thermal stability. And also it possesses crystallinity property. Okay. And it is resistant to UV radiation, so you can have large amount of applications. Okay. High energy radiation, most chemical and solvent, they are resistant to it. Okay. It has high dielectric strength. It can also be used in electronics industries. It has low water absorption, just like all other polymers. Absorption is less than 5%. Then applications. So how to generate this power by applying the pressure? Okay. So you can have like this in the first figure, you can see we have installed in the sidewalk. Okay. Or crosswalk while pedestrians are walking on the crosswalk or on the sidewalk. If we lay this, and whatever energy is produced is stored in the lithium batteries. The other side, in the mobile keypad and keyboards, you can install this. Whenever we give a pressure, what happens? This energy is produced and can be stored in a battery, lithium battery. Can also be laid on gym and workplaces. So vibrations on the gym machines while you're walking on the treadmill, so you can store that energy. In the workplace, in the chairs, you can lay down this for storing the energy and you can store the energy. And in the vehicles, you can have on clutches and gearboxes. What are the advantages? Unaffected by the external electromagnetic field, there is no pollution, no maintenance, easy replacement of the equipment. Okay. This is piezoelectric equipment. Okay. They cannot be used truly static measurement. That is the disadvantage. Can pick up stray voltage in connecting wires. Yeah, it can also pick up the stray voltage. Crystals is than whatever pressure is required is given. Okay, may get affected by high temperature on long usage. Everything has its own durability point, right? Then specially designed road which can then generate electricity. So car traveling, walking, and everything. So we can lay down here, which can pressurize it when uh, wheel rolls on it. Okay, so you can have the pressure, and from that you can have electricity. So you can have the street light from that. So I can say that piezoelectricity can be a revolutionary green energy source for the future. Okay, so it is flexible. That is, it can just by applying mechanical force, strain, stress, you can produce electricity without any pollution, right? That's a great advancement. It is a sustainable energy. it can convert ambient vibrations into electrical energy, and this electrical energy stored in the battery can be used for later applications. Thank you, students. Let us meet in another session on smart materials. Thank you.